This time we're going to look at the interaction of forces with energy graphs and how we can use them to tell some stuff. So the definition of potential energy, remember, is that the change in potential energy is minus the work done by the conservative force, which is minus F times delta X. And we're being fuzzy here, but I'm going to less fuzzy in a little bit. So we're taking right now the naive case. We can then say that the average force is minus delta U over delta X. But we've played a little fast and loose here, and implicitly, if the graph is not just a line, then I'm assuming that F can change. So really, we're talking about infinitesimals, and we should take a derivative which is the slope of the tangent line, rather than just a delta U over delta X. So really, we end up with that the conservative force at any given point is minus the slope of the graph. All right, that we can end up saying that we can look at a graph, and at any given point, the force acting when the object's at that point is given by minus the slope. So for instance, at how many places can we find the object in dynamic equilibrium? Take a few seconds, and then we'll do it together. Dynamic equilibrium means that F equals 0, but that means the slope equals 0, so we're looking for extrema. So we're looking for here, nope, that's a lie. Looking for here, or here, or here. So the answer is 3 times. There are 3 different places in dynamic equilibrium. What happens at the intersection of E and U? What does the particle do? What does it do next? Well, when E equals U, then K, which is E minus U, equals 0. So we have a turning point like we talked about before. And now we can see why it turns there. Because the slope, for instance, on the left, the slope of this line is negative. So the force is positive, and it is accelerated that way. So as it comes in, it's getting slower. When it reaches here, it stops, and then it's accelerated away. It turns around. And likewise, over here, the slope is positive, so the force is negative. It is accelerated that way. So an object coming in gets slower, stops, and then is accelerated away. All right. So we call a place at an extremum, we call it an equilibrium point because the force is 0 there. We call it stable if the particle at that point tends to accelerate back towards that point, and unstable if it tends to accelerate away from that point. So if we look at, for instance, this point, if we were at this point with this energy, we would have some kinetic energy and we'd move maybe this way, but as we did that, we would get slower and then be pulled back. Once it gets to the equilibrium point, it will be accelerated the other way, and so it's always being pushed towards this equilibrium point. If we could put it at this energy, it would stay there forever. If we could put the thing at this energy exactly, and we placed it here, it would also stay there forever because the force is 0. But if we have even a little bit more energy, if we nudge it just a little bit, we can see that in this case it's being accelerated away on the right because, again, negative slope is positive force, so it gets pushed that way. But it's also being pushed away on the left because positive slope is negative force, and so it gets pushed that way. So in this point, it doesn't stay there. You can put it there at rest and it will stay, but any deviation means it runs far away. Now, on globally, of course, this one will run until it hit here and come back. So it does eventually revisit that point, but not because of that point, but because it hits a potential wall and comes back. It's not attracted to that point. In fact, it's repelled. Unstable places are places where it's repelled. All right, we talked about this graph earlier, but notice that the equilibrium points depend only on the shape of U. They don't depend on the energy, but you might not be able to get to all of them. All right, if the thing has this energy, then it can't access this equilibrium point because here, at least if it's on this side of the graph, because here it will turn around. It will get stuck in that region, and it can't access this other region, unless in a quantum mechanical system it could tunnel down to that region. To wrap it up, the important physical implication is a system will accelerate so as to minimize its potential energy. All right, people like to say that systems prefer to have minimum potential energy, and that's true. Systems accelerate towards their minimum energy, but due to inertia, they often overshoot. So be a little careful about this. They're not always headed towards there. They're always accelerating towards places of minimum potential energy.